Okay, so I will try to present it. I'm sorry, maybe I will have some problems with voice, but I will do my best. So my keynote will be on a hybrid optical wireless communication systems. And it's not only mine work, it's work from my team and as well from the teams. We are very good cooperation, especially with Northumbria team, with FARI, teams in Spain, in Valencia with Professor Beatriz Ortega, in Las Palmas, Rafa, and the others, which just form our European group, ECRN. So at first, let me introduce my team. I'm from Czech Technical University in Prague. So my team is devoted on wireless and fiber optics. And currently we have 4 postdocs and time to time 5 to 7 or 8 PhD students and number of master students. As I mentioned, we are not only restricted in the Czech Republic, but currently we have bigger team, which is ECRN, European Network, Collaborative Network, which is excellent group of several teams, mostly from Czech Republic, UK, Spain, Portugal, and we just share PhD students. We have weekly meetings, we discussed everything together, and we try to just boost together our research, not only in single team, and there is very strong cooperation, and the students like travel in several teams just to set a setup, measure there, and just proceed the data at home and boost their growth considerably. Let's have a look on the topics we cover at the moment, which at first I will discuss just only the pure technologies, and then I will have a look on the combined technologies. So from visible light communications, historically, we just focused on device-to-device communications. At the start, we maybe just try to even fast data rates, but then it was seen that it is much higher application, not in high data rates, but mostly on the sensors and even for localization. So then now extremely spread is the topic for the optical camera-based communications. I will not discuss more in the detail because tomorrow you will hear more from the better specialist Othman. And then as well, we focus on relying between the nodes, sensors. Everything goes together with applications. So usually you should have a look on a specific cases. We had a very nice experiments for manufacturing, especially just to set some equipments and test inside the hospitals. We tested transmission even in a brain surgery room, and we tested with HHI from Germany, MIMO system, which could just send the data. Then for medical as well, for just healthcare, now it's very topical sensing. We as well covered intelligent transportation systems, and last not the least, last meter wireless access. Regarding free space optics, which is mostly based on lasers, we just started maybe 15 years ago by first light test, trying to find some atmospheric influence of the free space optical links, but then we stepped on relying, and then we continued for some maybe space on or laser to UAVs. Now very topical is just area of quantum key distribution when we started to have first experimental even results. And then because we like not to go very easy way, so we try to combine just to get the pros from many kind of technologies. So then we focused mostly on hybrid schemes. Hybrid with VLC, so combining free space optics with VLC, RF domain and VLC, just searching which one can bring more. And then as well, we combine free space optics with RF domain. We open with topics some microwave photonics parts, and then we even combine RF, free space optics, and VLC. Part of it will be just included in my presentation. So historically, one of very huge European project was Vision, European network, which just collected people in VLC in Europe a couple of years ago. And we were lucky that we were there involved. And it just covered 15 PhD students. They started to cooperate and create networks. And as now we are in a Chilean conference, so I saw two presentations from Vicente, which just originated from this project. And here you can see members of this Vision project. It's finished approximately 1 or 2 years ago, and the last student defended 2 months ago. So all 15 students defended PhD thesis with very high numbers of papers and very good research done. Now in Europe, it's running another very big project focusing researchers from free space optics and optical wireless. Even teams out of Europe are involved there. This project is a European network for, it's a NEWFOCUS for new technologies for optical wireless communications. And it started in 2020, and it still is running till next year. It's divided in 4 working groups based on the distances for optical wireless. First working group is devoted for ultra short range. It's a very small group because usually it goes for distances up to, let's say, 1 meter or on chip or device to device. Then there is working group for short range, mostly on indoor range, VLC, visible light positioning, and the sensors. The third working group, which is led by myself, is devoted on medium ranges, which is from hundreds up to hundreds of meters, which is devoted mostly for transport systems, underwater communication, terrestrial systems. And the last working group is on a long-range rings, which is led from the DHLR, German Aerospace Agency. And this is devoted for Earth to space, Earth to UAVs links based on optical wireless communications. This project is excellent, especially because pays all the traveling for researchers between teams for short-range missions. So the students can travel between teams. We always prepare them setups for measurements. They just come to our teams, or even from my teams travel to others. They perform measurements and then return, proceed the data, and just it boost on both sides, on sites of visits, or even on hosting, because they just bring them new stuff to do the research. Recently, we started a new European project, ON6G, which is devoted to combine optical wireless and RF domains within the sensor networks. So it started 1st of September, and actually it covers 10 PhD students. Now footpath of the Chilean is even more and even bigger, because what I've known, we at the moment accepted 2 students from Chile, which is Raul Zamorano and Francisco Rau, if I'm not wrong. And here you can see the members of this project, and there are even big industrial partners like Max Linear or Eblana. Mostly it's like devoted to combine RF domain and optical domain and create new sensor networks. Here you can even see some list of the topics, and it just goes to even out of our like research areas, opening topics like digital twins or wireless networks for 6G scenarios and so on. Now, if I have a look on just alone technologies, let's starting from optical camera-based communications. Tomorrow you will have a full presentation, so I will not go more into detail. Usually in optical communication, we would like to use just to receive from any type of transmitters, either display screens, LEDs, or arrays, using cameras and using the lowering shutter or global shutter. In our team, we started with just using just even testing the movement of finger and just communicating by OCC together and distinguish the movement of different shapes of the finger over the mobile. And then we moved even with cooperation with teams from University of Las Palmas and Northumbria to some arrays, flat arrays, and using a camera with different type of sources and distinguish them. Then even within that vision project, European project, we started with organic LED LEDs, flexible LEDs, which can be bent over, for example, pillars in shopping malls, or we can use big LED panels. So we characterize them and analyze them. Even we simulated how they can be just placed inside the shopping mall to have the better coverage. Here you can see part of the experiment when we tested how the performance of OCC is changing when with different radius of bending of such flexible organic LEDs. In the morning, you could see some results from the experiments. We tested this kind of curved OLED source for non-line of sight tests and just distinguish if it is capable. We go further even just to test several transmitters using non-line of sight. Another research which is inside the visible light communication is using radiating optical fibers. Usually it can be used only like signatures for in cars, in traffic marks, or even in buildings, and even for variables. On a picture, I don't know if you can see my cursor, you can see a radiating optical fiber, which is just fed by LED, and it illuminates along the wall, along the all length. It radiates. Usually it's done that there are some scattering particles inside, so comparable to the classical optical fibers. When you have total inner reflection here, the light is radiated off the fiber along the structure. We just send the data to this fiber and read it by the camera and proceed the data. Clara, who is just now currently in a room of the conference, tested it starting from her master thesis, and now she continues in a PhD thesis. We reach even, we can read it even up to the distance 40 meters. And tomorrow, in very excellent presentation, Clara will show you how this kind of the transmitter can be used as the variable. If you just put it just on a t-shirt and test it and just have it as a transmitter on your body. We as well tested car-to-car communications, but it's not more related to hybrid system, so I will just only mention this scheme when we had two headsets and just even created artificial noise and try to distinguish from the communication. We tested cameras even for longer distances. Here is just a sketch from our experiments when we had 400 meters link, where Elizabeth from Northumbria tested in Prague this connection, and we even performed very good link performance. Another research based on a VLC was using on-body sensors. Here you can see simulations of the people who has several sensors, which maybe can just measure his body activities. He has two nodes, one on a shoulder, one in the middle of the body, which connect the data from sensors, and those nodes can be connected to the transmitters or receivers on the ceiling of the hospital room while he's moving. So using simulations, we tested if it is possible to use only visible light communication to interconnect nodes and this person to the ceiling. And the results were very positive. Then now focus on free space optics. Historically, at CTU, we had one single link which were connected to buildings where we measured atmospheric influence on the building, but then we extended for another two links. So we here have some small star scenario, but usually in outdoor links, you cannot expect that particle turbulence happen when you would like to. So it's better to have your laboratory equipments. So that's why, based even for first measurements I've done as a PhD student in Newcastle, we establish a turbulence chamber even here in Prague. So we can create it a 6 meter long chamber and test turbulence, fog, and its influence on the free space optics. Together we can add RF circuits, and you will see how this combination of RF and free space optics works together. We tested fog, dust particles, turbulences. At the beginning even rain, but this doesn't have too much big impact. Here you can see some historical pictures. On the top you can see where we tested parallel links with different turbulences, different correlated turbulences. We tested in fog. Even we tested some dust particles, and then we extended this experiment in Northumbria with the dust chamber. So the dust particles were just floated in a turbulence, and we just analyzed their effects. For classical links, you can use diversity schemes just to improve the system. So here there are several methods which we tested, and one of them, especially for fog or even in different schemes, is using the hybrid techniques. This is where first time we just came to use hybrid, the word hybrid, where we use RF domain to bypass when fog usually attenuated link enough, and we were no other option than to reconnect to RF domain. From free space optics, just some current research. Now you can see we just move to adaptive systems which are switched online in time. This is not any like post-processing. So together with Zoom and Carlos, we are doing switching. We have done switching. It was done last year. Experiment switching in turbulence in fog, fast switching in free space optics. This is some old, we even not even switch, but we even do a reconstruction of pulses. This is from an experiment when we regenerate pulses 10 gigabits per second using some kind of homemade regenerator. And last from this direct technologies, we started to measure quantum key distribution. Here you can see some parts of our equipment and a setup where usually you have your data link, which is done on the top, and the encryption, and then on top of it, you have you send the keys using quantum key distribution. Typically, we work with entangled photons. We just create entangled photons for this quantum key distribution using spontaneous parametric down conversion, when a single photon is just divided into the two tangled pairs, one pair of tangled photons. Usually they are polarization entangled, and we test if droppers just send the quantum just of the key and just then change the parameters of the photons. Okay, so this was not very short, it was shorter start, and now let's have a look on hybrid schemes. At first, I would like to start with combination of free space optic and VLC. So typically, the main idea why to use it. So we would like to, sorry, can you hear me?
Yes.
Okay, I just had some noise, so I have some echo, so I'm sorry for it. So typically, the idea is to have everything in an optical domain and a wireless. And in a city, you would like to connect, for example, buildings by free space optics. Then you should have some distribution to the rooms, and inside the rooms, you use VLC for communication between the transmitter and users, as well as you can use VLC for precise positioning for indoor. Another idea is to use free space channel outdoor communication, either to connect ships and then inside the ships you can have the coverage using VLC, or which even was tested is that you are using free space optical channel to either satellites or high altitude flying platforms or all that kind of aircrafts, and then inside the communication or just connection can be done by visible light. The same is even now can be implemented in concept of 5G and beyond networks. Here on you can see that the connection between the particle nodes can be done either in millimeter waves, which was the older part, but now even is switched to free space optics, just to allow less losses and even higher capacities to be just there. And then as a combined principle, VLC has been just even established in a standard, so it could be done there as from the nodes towards the users. Here you can see another scheme of the same, when there is just shown it in a free space optical and VLC parts. And then let's have a look what we have done. At first, we tried to just even have a look on relying. Usually, you just couple several links, so you have to see what's your total performance is. So typically, even in the room, we try to use not only transmit a single link from the source, but in case when someone is not connected directly, or there is some obstruct which just blocks the link, you can use another node to rely. There are established even enumerations how to find or how to use it. You can use either direct forwarding. You are just only in kind of reflection. You do not process the data or even a signal, improve it at all. Or you can use this node if it is really receiving the signal, it can somehow improve it. Either amplify and forward, or even decode, correct it and forward. So in our paper, we just have a look on these schemes when the users are moving in the room and they are using amplify and forward and decode and forward method. Here in equation, you can go deep in when you just open our paper. So we just search what would happen if there is transmitter on the ceiling, which cannot be connected to the end user, but is using a relay node. But in reality, no one is always ideally just pointing to each other. So let's have a look that the relay node is not not just oriented directly to the transmitter, neither to end user. So it can be just randomly oriented, and it stands in particular part of the room. So we tested what happens if we change the orientation of relay node and user, and in just for particular places inside the room. Here is part of the simulation where we just change, and usually we could see that amplify and forward brings very nice results. If, of course, decode and forward is even better, but not always you should use the most difficult approach. Sometimes even amplify and forward, it's enough to improve the bare performance. The same what we tried, for example, when we improved the transmit power a little bit, we extended the possibilities of the placement of the relay nodes. Then, as my team is usually not, even as people in my team don't like to do only simulations, almost everyone is more experiment-based, so we try to set this experiment. So on a figure, you can see on the top scheme when we had a relay node and we amplify, it's amplify and forward. So there was one channel, then we received the data, then we amplified the driver and then forwarded. Second case was when we received the data and when we decoded, it was done in MATLAB and then again forwarded. So usually this was experimentally that's shown that on a figure downstairs, you can see in some cases, even link, which is 0, without relying up to 5 meters, or even can outperforms the amplifier and forward. It's not necessary to amplify and bring another noises. For longer distances, then it's fine. And in our cases, decode and forward, it's a winner one. Okay, then we just went to our hybrid scheme. Here we use MCAP model, MCAP modulation, and we transmitted it over a free space optical channel, and then received, and then again use it as a signal for the driver, and transmitted it using the VLC channel. This actually simulates the case when you have free space optical channel between buildings, and then you receive signal is then distributed to the users using VLC. Here you can see some results. Usually we tested it even for different distances, and for free space optical links, we tested for different turbulences. If we are capable, even in harsh outdoor systems, then in indoor using VLC received some good results. Now let's focus on another case of a hybrid scheme which combines visible light and using a photodetector and part of visible light optical camera-based communication which use image sensor. So comparable to previous case, when usually you would like to transmit high data using free space optics and then visible light, combining for visible light and OCC usually is very beneficial for indoor applications or sensors applications, and for camera and for sensors you don't need to just transmit very high data rates, and then you should handle how to combine both, how to use high data rates together with low data rates. Usually you don't want to have, or users don't want to have at all so much technology. They would like to have only one equipment, and even the simplest one, but they do not want to switch and just to wait if something transmit data then another one. They would like to use both at once. So to use low speed OCC and high speed visible light. Here you can see scheme when inside of the building or of the room you have hybrid optical lanes when your LED transmit both fast data rate and slow data rates. Fast data rates for internet surfing, maybe to some sensors, for example, transmitting maps or whatever to some vacuum cleaners when they are not capable to create their own, or to television. But on the other side, now our work is completely occupied by a lot of sensors. So you can just bring some commands to the sensors to be switched on and send the data to activate whatever, and so on. So that's now what the challenges are for such kind of communication. You can see that the main is the difference in bandwidth for using both VLC and OCC. So photodetector versus camera, but even the constraints of the systems of the data itself. Usually you need LEDs or transmitters with different switching speeds for VLC and OCC. And as well, there is increased level of interference between using different LEDs, and which brings on top increased complexity. So in literature, you can see different solutions. First one just used in the data. Usually in once they used Manchester coding, usually for diming, and on-off keying. Usually when there was on, they just modulated that on by VLC signal. Immediately you can see drawback of the system is that they are not using off part, so there's very low bandwidth efficiency of such kind of system. Another solution was to use intensity shift keying and multi-level on-off keying. So envelope of this multi-level just was used for OCC, while inside there was a modulated VLC signal. It brought another problems usually with the data processing, and especially the varying of amplitude depths usually just brought another errors to the systems. What we proposed in our first solution was to use bipolar multi-level on-off keying, so which was modulated, and then especially But at the first sight, we saw that there's some drawbacks using some biases, which needed to be solved. So it was published in the Internet of Things journal, and its topic was developed by Shivani. And so this is slight overview of the system. And here you can see we just on the transmitter side modulated together OCC and VLC data, and then just use arbitrary waveform generator and bias T and LED and transmitted data, and which was received by both by camera system and FIDI photodetector, and it was all data was just processed separately. On the side of OCC, there was a region of interest and just processed the data. In VLC, there was some thresholding and just filtering of the data. What I mentioned, the problem was using the bias T, which actually behaves as a high-pass filter. So usually here you can see normalized amplitude, and on a figure, this high-pass filter, what just creates in your received data. Usually we can see this effect in smaller frequencies. If we try a transmission at 1 megahertz, this effect is completely removed. But if we just go to typical transmit data rates or frequencies, it's a big problem for us. So to bypass this effect, the solution was, instead of using just pure unipolar solution, which is in the case of A figure, we started to do some kind of overlapping. So this way we enlarge the amplitude of the pulses of the, but it just brings there some overlapping, and we tested what ratio of overlapping, how it influences both transmission of the OCC and VLC signals. Here you can see OCC pictures for different amplitude of overlapping. And here are some statistics. For example, on the left side, you can see how bitrate for VLC is changing when you use different bit rates for OCC. And it can be seen that it has quite high impact on it. The same, even we tested how OCC is changing when we use different VLC, and usually as well, you could see, but not as high impact as in case of VLC. To improve the system, we just went further, and we just remembered on one of our papers, which had Peter Chvojka in 2020, when we just used direct modulation of LED of the chip. So in that paper, we just used it to some polarization multiplexing to have 17 gigabits per second VLC, but here we just use only the technique, not to reach high data rate, but just to avoid to use bias T. And we directly modulated LED and just tested. It surprisingly allowed us to improve the data rates almost twice, and even it improved the OCC performance. Here you can see on how it was with bias T, and when we get just remove bias T and directly modulated LED, and the improvement was really very high of such kind of system. Then as well, we just solved how to proceed to the OCC data, but now maybe I don't have enough time. I can return to this part maybe later. So usually this hybrid schemes allows us to use both one transmitter to transmit OCC and VLC signal and to be received. So it's kind of SIMO setup. Possible extension, because we tried it only on some wavelength to extend to different wavelengths and to test for different ranges and orientations. We tried even in a half of the experiment with this at the time when we use BIAS-T to set it for some kind of application. So together with colleagues from Valencia University, was just a research mission in our team. So we tried to set the transmission over a polymer fiber and then transmission of the system of the signal. Here you can see the setup. So it's almost similar as previous, but we set there the kind of the application when we transmit the signal in a building using polymer fibers, and then using some kind of lens, we receive it by, in case of OCC and VLC, and again we process the data. So we use that setup and we just perform, and the application showed us that it can be used very well using this kind of optical fiber and the scheme itself. So I will maybe skip these results. There's no time for it. Then what we just saw is, okay, everyone is just only doing kind of downlink. What if we use it even for uplink? So here is the scheme which we used. And the idea was that we have kind of sensor which should be initiated. So for downlink, we use only some commands using OCC. So that kind of sensor has camera everywhere. So the signal is transmitted using polymer optical fiber and transmitted on ceiling and received by the camera OCC signal. And then from the user, it has, for example, sends a lot of data and they are transmitted uplink. So it's kind of reverse. So the data from cameras, videos are transmitted uplink using LED, received by using some lens, and just transmitted via fiber to the received part of VLC. So we performed this experiment, again, focused on the OCC part, tested it for different distances, and then we have a look on VLC of how it's influenced for different modulation formats. So now it seems that this kind of setup is possible to be implemented. As I showed to you before, we even work with different kind of fibers, and now maybe we even would like to just move from this polymer-based fibers to radiating fibers, which can be used even in better applications. So it was the combination of VLC and OCC. Now I will switch a little bit off the topic of conference. I'm sorry, still keep VLC, but later on I will even leave this VLC. So now we combine this optical domain with RF domain. The previous presentation was very nice, how the RF systems can be implemented and combined. So I'll just only mention one of our analysis. We just tested the combination of device-to-device systems. Usually when you communicate directly, you don't use the network itself, but communicate directly between your mobile phones or your equipments. And now we analyze what would happen if you have two possibilities. Either to use RF domain to device-to-device communication or used VLC between devices. We tested it in the room. There were just, the idea was there are numbers of these couples doing device-to-device communications. They are differently just distributed in a room with different orientation of the devices of transmitters towards each other. And there they were like using both technologies. So for RF, you could have much wider radiation patterns, but on the other side, it's maybe not so energy efficient. And the colleagues, and especially there was like devoted colleagues from the Department of Telecommunications, and we work with them. So they were just mostly from the networking, and they will just have a look on energy efficiency, either when you are using RF domain or RF or VLC or optical domain. On the first graph, you can see how it looks like when you just are using what's the outage ratio is when you are using pure RF. This is the green one. Then there is purple. I think it's VLC, and when you have possibility to switch between them. We set different scenario how to switch between the technologies, like randomly, or there was proposed model for the switching in the paper, and how the outage is improved. Figure A shows when always they are facing each other. Phase B when randomly in particle angles 0 to 30 degrees, and C is randomly. And N is a number of device-to-device couples. The same, we tested how the capacity in such kind of the overall capacity in this scheme in between those device-to-device networks is improved. You could see that RF domain usually works only for just very small number of the couples, but usually visible light communication was better. But if you optimize it, you could get even 7 times better capacity and the switching between the technologies. The same, what was the main impact of this paper was to find energy efficiency. It means megabit per joule. So we recalculated, our colleagues recalculated, and again, it shows that the visible communication is better in RF, but when you are just possibility to switch between, even that efficiency goes considerable better. And now the last part of the hybrid schemes shows radio over fiber and free space optic microwave photonics. Usually the idea is to bring the data to some node. Now it's moving, so even by optics from the centralized pool when they are using we are using a lot of resources inside. They are just using only a fiber to bring the signal to the node when there is retransmitted in an RF domain, now even in millimeter wave. It can be bypassed, not fiber, but even you can use free space optics in this case, but you have to know how to modulate it. Typically, they are using direct modular or optical heterodyning when the signal from 2 lasers just mixed on a Mach-Zehnder modulator with the data, and then you are using the differences between those 2 lasers, or you only just modulate only 1 laser. The better modules even just brings up conversion when you are just using 1 Mach-Zehnder for carrier, 1 for data. You suppress carrier and you get twice a bigger frequency. So in historical, they just transmitted up to terabits per second over even optics. This is what we have done. laboratory experiments when we started with a transmitter of 25 gigabits at 25 gigahertz over free space optics modulated, and we even tried it. Usually now this free space optics is done that you couple from fiber directly using lenses and you transmit the data. So we transmitted over 40 meters indoor free space optical channel. Then we even use RF domain and transmitted RF signals. In the frequencies, we went from 25 to up to 39 or 60 gigahertz and transmitted up to 100 meters. And even we tested outdoor between the buildings. And then we retransmitted in RF domain to end users. So even for this one, we developed antennas, optical beamforming in optical domain and RF domain, so combine optical and RF. And here you can see some design even for some antennas arrays and lasers. Last part of our research is focused on hollow core fibers, where we work together with Southampton University. And these are very interesting because you can use air in the fibers, so which is faster for data than to use silica cores. And this can be used even combining RF domain and even free space optics. So this is area where we are just now focusing. We have a new grant for this to extend it to RF domain, even for free space optical domain. So now to conclude my presentation, so hybrid systems can usually bring you advances from all domains you combine, but you should very wisely just select which one can be used there. But even in a future world, you will not avoid, and all the technology I think would use pros from number of them. In a hybrid VLC-OCC systems, usually for indoor domains, can be used for sensors and data transmission, and a hybrid RF and free space optical, it just brings another advantages for the outdoor applications. Now we just try to combine them, and even in that new project, we try, for example, to create digital twins to just select the data from all and just to switch in between the technologies to foresee some crisis situations, for example, in a transportation and so on. So it's slightly end of my presentation. I would like to thank you for your attention.